Okay, welcome back. This is lecture 10B. Let's get the screen up there and let's show from current slide. Take a minute here to display settings, duplicate slice. Okay, so let's go. So we're going to take back off where we left off in lecture 10A, which was we got to the momentum concept. And so far we've gotten a tool called continuity, which is based on the conservation of mass. We've got the energy concept, conservation of energy, which we've developed from law of thermodynamics. And now we're going to get into another conservation of momentum concept. And out of that, we're going to get an equation that describes the bed shear stress, which we're not going to use a lot in this class. We're going to use a little bit. But more importantly, it's on our way to getting at what we call the flow resistance equation. And the kind of the biggest equation you're going to use in open channel hydraulics consistently is something called the Manning equation, especially in the United States, or the Shazy equation is what they use in Europe. Sometimes we use it in the US, but predominantly the Manning equation. So if I look at the conservation of momentum concept, we start with Newton's second law, which says that the summation of external forces on a system is equal to the rate of change of the momentum of the system. So if I've got the external forces, the summation of those, and I look at the change of momentum with respect to t, with respect to the time. And so if I look at momentum, that's nothing more than the mass times the velocity. And so we're looking at, okay, on this system, what is the change of that momentum with respect to time? And that's equal to the external, the sum of the external forces. If you want to look more at Reynolds transport theorem, you can look at lecture 20 from my fluid mechanics course notes. I've posted that in Canvas for our module for lecture 10, and so you can see that there. And so if I use that Reynolds transport theorem, which I talked about a little bit earlier when I was talking about continuity, we can look and say that the change with respect to time of this system right here, that's equal to the sum of the forces on the system. So this is the momentum transfer changes. And so we can then further and make some simplifications, assuming steady flow, using the Reynolds transport theorem that says that the sum of the external forces is equal to this change of momentum as expressed right here, which is rho. Beta is a momentum coefficient because, again, as I explained earlier, we're going to use mean velocity. And that mean velocity, once you start squaring it and doing things to it to get at something, in this case, it'd be a momentum. We don't do a very good job if we just use the mean velocity. So we end up using something in order to correct for that mean velocity, which is this Boussinesq coefficient. And then we have the area concept here, the area. This is all derived. You can see this in this lecture 20. And so we've got the downstream values designated by 2 and the upstream by the 1. So we're looking at the sum of the forces external in the x direction is equal to this difference in the momentum flux with respect to upstream and downstream. And so as we look at this, if I start to look and apply this, so I've just transferred that equation to this slide right here, and you can see that if we, what I'm doing is making a simplifying assumption, just in this particular case, saying that this Boussinesq equation, the Boussinesq coefficient is equal to 1, which says that the mean velocity does a fairly decent job of being used to calculate the momentum. And so if I look and say, okay, let's simplify this. We know that continuity says that the discharge is equal to area times the velocity. So we can start making some assumptions here, taking this V2A2 out of the picture, calling that Q2, or Q, because we know that Q1 is equal to Q2 in this case. And so we just call it Q, which equals to Q. And so we can come down here, we pull the value of the density through, and we pull the value of Q through there. And so we pull these out, and what we're left with is V2 and V1. So I've got V2 minus V1. And so the sum of the forces in the x direction is equal to this quantity here. All right, so we've got basically now we've got to look at the forces. And so what do we have? We've got what we call the body force or the gravity force, and that's in the downward direction. But we're on a slope here. We've got some slope theta. And so in order to capture that, this is the unit weight of the fluid, right? That's the unit weight. That's the gamma. And that has units of pounds per cubic foot. If I then look at, okay, that unit weight, and I multiply that by the volume that's represented by this, if I've got some cross-sectional area times this delta x, the delta x is this distance right here. So you can see that if the cross-sectional area is perpendicular to the slide that's in front of you, that's the A, the delta x is distance. So this right here is a volume term, volume times this unit weight gamma. You can see that unit weight in pounds per cubic foot or pounds per volume times the volume simply gives you the weight of that volume. And so then if I multiply it by the sine of theta, I'm getting the value in the x direction. And so I'm resolving that, and I'm calling this my x direction here, okay? So that's my weight force. Now I've got the resisting force on the bottom, and that resisting force is the bed shear stress tau 0 times P, which is the wetted perimeter, we've introduced that, times delta x. So if you think of that, it's basically the wetted perimeter, the value of, if you think of it volumetrically, if we were in class, I'd typically take a piece of paper and I'd kind of make that look like a parabolic cross-section control volume, and I could show you the wetted perimeter is the short side of the paper, and the delta x is the long side. And so if I fold that out, you can see that the area in contact with moving water is simply this P times delta x, okay? And so that goes as my shear force. So this is the shear force right here. This is the weight force here. And then I've got the hydrostatic pressure on both ends. So we've got water, again, with any kind of a control volume or control surface, you got to cut it. You replace it with a force. So I've got a hydrostatic force pushing back this way. I've got a hydrostatic force pushing this way. And simply that's a gamma A, from hydrostatics, which you should have learned in fluid mechanics, gamma A, which is the cross-sectional area, times this Y value, that gives me the force on the upstream. So this is the hydrostatic force upstream, and then gamma A times Y2 would be the hydrostatic force downstream pushing back. So I've got all the forces captured there. Now, if I think, and getting rid of sine theta, that's nothing more than this Z1 minus Z2 over delta X. Delta Z is this Z2 minus Z1. Delta Y is the Y2 minus Y1. And delta V is the V2 minus V1. If I look at these abbreviations and put them in here, substitute them into this equation above, I end up coming up with this form right here and pulling through the shear stress. I end up having this long equation here where I've got delta Z, delta X, delta Y, delta X, delta V, delta X. So if I look and I transfer that to the next page, and I remember from calculus that if I take the limit as delta X approaches 0 of this, which is what I'm doing right here, I end up coming up with a derivative, right? And so I pull the term alpha, gamma, and the hydraulic radius. Remember, the hydraulic radius is the area divided by the wetted perimeter. So here's the hydraulic radius, here's the hydraulic radius, here's the hydraulic radius. You can see the gammas there. So I pull those through the brackets here, and I end up having the limit as delta x approaches 0, a delta z over delta x, a delta y over delta x, and delta v over delta y. And so I can pull through and say, all right, again, if that limit approaches 0, I end up having the derivative. So I end up having gamma r times this. And then if I say, okay, well, this is all the derivative with respect to x, and I can play a game here with this, and I can move some things around. This ends up becoming, just do a little calculus trick, becomes v squared over 2, all right, 2g. I can then basically pull the derivative through, and then I'm having z plus y plus v squared over 2g. Well, this is nothing more than the total energy, right? This looks just like the energy equation. And so if I go through, sorry about that, I'll pull that up. So again, this is the energy per unit weight of fluid. And now, as I go through my momentum equation, I've gotten to the point where I can express the bed shear stress in terms of minus the unit weight of the fluid. So this is unit weight. This is the hydraulic radius. And this is the derivative of the total energy with respect to x. And so again, if I go back the other way and I say, all right, well, that can be expressed, this delta E over delta X, that's nothing more, this dE dx is nothing more than this delta E over delta X. And you can see here that this is my delta E, this is my delta X. Well, what am I talking about? That change of delta E with respect to delta X is nothing more than a slope term, right? So that's the friction slope. So if I look at this, I end up calculating this. This is my equation for bed shear. This is what is used. This is a very important term to remember here. This is my bed shear stress. So this is, I can go along at any point and I can say, what is the bed feeling? What is the shear stress? This is what the shear stress is. It's equal to unit weight times the hydraulic radius that I would have at that point times this friction slope. This is very powerful to do a number of things. A lot of them beyond the scope of this class, but it's something you should remember. We will use it in lecture 11. All right, so I want to make another definition right now, and that's called the shear velocity. And I just want to restate, or I want to state that the shear velocity is a term that's has length per time as its units. That's why we call it a velocity. It's really not a velocity, it's a measure of the shear stress, but that's nothing more than the bed shear stress divided by the density of the fluid, the square root. And if you look at this, this is pounds per square foot. This has units of mass per cubic foot. If you look at this, you come out, and this has units of length per time or feet per second. And so if I know that the bed shear stress is gamma R S of F, and I divide by the density, that turns out to be G R S of F. Now this is a term that we would use, and you'll use it at times in other things, especially if you get into looking at sediment transport or anything where you're moving something with flowing water. Shear velocity and shear stress become very important. All right, so that's another equation that's important. That's the equation for bed shear stress. Now I want to take you to this flow resistance equation. And remember what we're looking at here is we want to describe the velocity in terms of something. And so that's what we're after here, using this flow resistance, or developing a flow resistance equation. So I can look at dimensional analysis. And if I look at dimensional analysis, which you may or may not have covered in fluid mechanics, but that traditional dimensional analysis is what we use a lot in experiments in the laboratory, where we would say, if we're interested in shear stress in this case, what are the properties? What would we be collecting as data to characterize that bed shear stress? And so we do that dimensional analysis, we find that we would be looking at the property of velocity, the property of the fluid density, and then this becomes a coefficient of friction that basically allows you to go from a proportionality to some expression of quality between the two. And so essentially we can say that the bed shear stress is equal to this friction coefficient, resistance coefficient, times the density of the fluid to the velocity at the second power. And this is something that we'll mention here in the next slide that, well, actually it's at the bottom of this one. We actually see this empirically when we look at flume or field measurements. We can calculate the bed shear stress, we can measure the velocity, and we see that they're proportional. The square of the velocity proportional to the bed shear stress. But let's go back up here in the slide and we can manipulate things a little bit. We can solve for the velocity, and we can see that the velocity is equal to the friction resistance coefficient times the square root of the bed shear stress divided by the density. Well, that is nothing more than the shear velocity, right? We've already defined that. And then we further define the shear velocity as equal to the square root of g r s sub f. So I can plug that in, and that becomes V is equal to the resistance coefficient C sub f times the square root of g r s sub f. That looks very similar to what you've seen in Darcy-Weisbach relationship when you've dealt with that for pipe flow. Now, Anton Chazy, when he was making measurements in 1769, he ran a bunch of experiments on the Seine River and concluded that the velocity is equal to this value C. We're going to call this the Chazy equation. And so it's value of C times the hydraulic radius times the bed slope. It looks very similar to what you see right here, right? And so Chazy's equation is sometimes written like this, where you've got, this is the form of the equation. Moreover, what we do is we get rid of the g's a lot of times, and it's just V is equal to C R S sub F to the 1/2 to the 1/2. Actually, it's put some lines in there. Let me rewrite that. So I've got, this becomes V is equal to C square root of R S sub F. Or it's also written sometimes like this. Now, there was a guy named Robert Manning. He was an Irish engineer. He did a lot of work, and he was trying to come up with a way to characterize C. And he basically said that his Chazy C values were 1.49 over the roughness, or known as the Manning coefficient, times the hydraulic radius. If I plug that into Chazy's equation, we end up getting this form right here. This is the well-known Manning equation. You need to remember this. You need to star this because we're going to use that a lot. And so if we combine this with continuity, which says Q is equal to AV, this is also a form of the Manning equation. And just to remind you, this is 1.49 over N. Area is A, R is the hydraulic radius, S sub F is the friction slope. Now, if we are in, this is in English units. If we're in SI system, this becomes Q is equal to 1 over N, A, R to the 2/3, S sub F to the 1/2, where this is the difference between the two. And so if it's in SI units, we don't want to have to change our roughness value. So the way we deal with it is we change this value of 1.49 to just a coefficient of 1. So if you look at roughness coefficients, you can see if you were to pick them, these are just basically, you know, this is not natural channels. These are metal, non-metal, you know, glass. You can see values for glass very low. We have a number of ways to get it. I've got in the lecture 10 module, you can see this report from Barnes. It's listed in there. You can see where we go through and we have pictures for various locations where we've actually measured flows, gotten the frictional, the friction slope, measured the hydraulic radius, the velocities, etc., and back calculated the value of N. And you can see these kind of studies where this is near New Cumberland, Ohio. This is Indian Fork. You can see this stream here, and they have a value N of 0.026. So this is, you know, this is from photo comparison. So then you can go through. These values were actually computed from real data, but you can, as an engineer, go through Barnes's book, and you can say, oh, okay, well, I've got a stream that looks like this, and so I know it's going to be somewhere in this neighborhood of an N value of 0.026. This is, you know, basically in Yosemite National Park. This is the Merced River. And so you can see this is a little rougher bed here. You see these cobbles and boulders and things. Here, this value is 0.065. Again, we went through and we measured the velocities, we measured the hydraulic radius, we measured the friction slope, and we back calculated the value of N. And you can see it's totally different. It's a much lower N value here as you compare it to the Merced River with these boulders, much higher. Here is for you know, floodplains, and this is a report by Arsenault and Schneider, and I listed it right here. You can look this up online. I don't think I have it posted in the module, but you can go to the USGS Water Supply Paper 2339, and you can get this for floodplains. And here you've got a value of in 0.12, fairly rough. So this is an area in southern part of the United States. This is in Mississippi. And so you've got a lot of trees here, and as water flows through here, maybe at this depth, it's encountering a lot of trees and obstructions and things. And so that raises this value of N. The higher the value of N, the rougher the channel is. Okay, so we also, that's photographic comparison. We also have some equations for roughness, for Manning's roughness. So you've got for gravel bed streams, a guy named Strickler developed a value or an equation to express the roughness, in value roughness as 0.034 times the median diameter of the bed sediments. So you get the gravel, you go out there and you do a sieve analysis, and you get a size distribution, and the 50th percentile of that size distribution, you plug that in and compound, take it to the 1/6 power, and you get the value of N. A colleague of mine at the USGS named Bob Jarrett, he looked at mountain streams in Colorado and some of the Mountain West, and he said he could express N as a function of the slope of the stream and the hydraulic radius you would expect to have. This is his relation, and it works. And I've seen some publications other people have done, some experiments, and it seems to work fairly well for these mountain streams in Colorado and the Mountain West. Again, I've already mentioned this, but the Manning equation, if you're using SI, remember, don't forget to use the value 1. This is something that students make a mistake. If I give you a problem using SI units, sometimes they forget. All right, again, let's take this a step further and let's look at uniform flow, because we're going to look at something called the normal depth or the uniform flow depth. And we're going to use the Manning equation to compute that. And so if I've got uniform flow, that means the velocity and the depths don't change with respect to distance, which means that the bed slope is equal to the water surface slope, which equals the friction slope. So if I look at the bed shear stress, and this is my equation for that, but if it's uniform flow, I can substitute bed slope in for the friction slope. And the same thing happens with the Manning equation. Notice that my Manning equation uses the friction slope here, but if it's uniform flow, I can substitute in S of O. This is only for uniform flow that I can get away with doing this. So I can't use the bed slope in replacing the friction slope unless I'm assuming that I've got uniform flow conditions. So again, we've got this thing called normal depth, also known as AKA uniform flow depth. And that's the depth of flow in the channel when uniform exists and when uniform flow exists. So again, uniform flow, friction slope, water surface slope, bed slope, those are all equal to each other. S of F, S of W, S of O. All right? And so we're going to talk about solving for something called the normal depth of uniform flow depth. This is going to be something that you're going to have to master. This is going to be something that I'm going to quiz you on the first part of this week. All right, so that concludes this lecture B. Lecture 10B. I'm going to give you an example problem here in just a minute as another module.